In this video, I'm going to explain the projections onto the subspaces. So first, I'll explain you the whole idea of projections, and then we'll solve the examples. So let's consider a vector space V, and let W be the subspace with the bases of B1 bar, comma so on till Bk bar, and X bar belongs to V. That means some vector X bar is in the space of this vector space. Now the problem we have in hand is how to find the orthogonal projection of vector X bar on this W. That means how do we find the projection of this X bar vector which is in vector space on this subspace W. So the diagram looks something like this. You have the vector X, this is the entire plane W. So I need to find two parts. That means I need to break X into two parts or two pieces. The first one is the projection of W on X. So I'm calling that projection of W on X bar. So this is the first piece that I need to find. And the second part which I need to find is X bar perp or X bar perpendicular, which is nothing but perpendicular to W. So that is that part. So I can break this X into two parts, PW of X bar and X perpendicular. So firstly I need to find PW of X bar, which is the projection of W on X bar. So let's see how we can do that. So I write the set of equations. X bar, the vector which is given to me, it has some perpendicular part X perpendicular, and then it has some non-perpendicular part which is PW of X. So I break this PW of X or expand it, and that is C1 B1 bar plus so on till Ck Bk bar, where Ck is the constant and B1 and till Bk are nothing but the bases in the subspace W. So X bar is basically denoted in the form of a linear combination of basis vectors B1, B2 till Bk, and a part of X bar is in W, which is this, and then you have the perpendicular part. That means the perpendicular part of X to W. So from this equation here on top, we can now find the perpendicular part, X perpendicular bar, which will be nothing but X bar minus PW of X bar. So once I'm able to find this PW of X bar, I can take this entire equation on this side, subtract it with X bar, which is already given to me. I'll get the perpendicular part, right? So that will be the orthogonal part, right? So let's see how we can proceed. Now I'll find the inner product of B1 with X bar. So remember that B's are nothing but the basis in the subspace W. So I'm going to take the first basis, which is B1, and then find the inner product of that with X bar. So this is the denotation for inner space or inner product. You have these two brackets. So I'm going to take this equation C1 inner product B1 bar slash B1 bar. That means I'm multiplying C1 B1 bar with B1 bar, right? So you have C1 B1 bar dot B1 bar. C1 dot B1 bar doesn't make sense because it's a scalar, right? So you have C1 B1 bar slash B1 bar, inner product of B1 with itself, plus next value C2 B1 bar. I'm finding dot product of B1 bar with the next basis, which will be B2 here. So slash B2 plus so on till Ck B1 bar slash Bk bar, and that will be equal to B1 bar dot X bar here, B1 bar dot X bar, and I'm finding the inner product. Now one of the factors which we have left is X perpendicular bar. So that's what I've written here on the left hand side. You'll have inner product of B1 bar. I'm multiplying B1 bar with X perpendicular bar, and that dot product is going to be 0 because X perpendicular bar is 0, right? So in every subsequent inner product which I find, the basis with X perpendicular is always going to be 0. So let's look at this in the next part. Now I'm going to find the inner product of B2 bar with X bar. So you have C1 B2 bar slash B1 bar plus C2 B2 bar slash B2 bar till so on till Ck equal to B2 bar slash X bar, and B2 bar slash X perpendicular will again be 0. So I can go on like this till Ck. So you'll get C1 Bk bar slash Bk bar and so on till this factor. Now these set of equations which we have written till K can be represented in the form of a matrix. So this matrix will consist of k equations, will be found from k equations with k unknowns. So the first point which we are going to write here is these inner products. So we have b1 bar slash b1 bar, b1 bar slash b2 bar, and b1 bar slash bk bar, and all that is going to be multiplied with c1 c2 till ck. So I have written c1 c2 ck. Similarly b2 slash b1 bar and so on till bk, these will be multiplied by this, and the last factor with k multiplied with this. That will be equal to nothing but whatever we did on the right hand side, b1 bar dot x bar inner product b2 bar dot x bar till bk bar dot x bar. Right? Now we'll represent this matrix as some matrix A. So therefore this entire process becomes A into C1 C2 Ck equal to this matrix B1 bar slash X bar, B2 bar slash X bar, and so on. Right? Now what I'm going to do is I'm going to keep this C1 as it is, and I'm going to find the inverse of A. So I'm going to bring A on this side. So the equation becomes C1 C2 till Ck, A inverse into this matrix consisting of inner products of bases with vector x. Now from here there are going to be some special cases. So let's look at the first special case. If all b's are orthonormal, that means all the bases are orthonormal, in that case A, the matrix A, just becomes an identity matrix. So A inverse will be I inverse, which is nothing but identity, and once you have an identity matrix here, C1 C2 till Ck becomes nothing but the dot products of b1 bar slash x bar, b2 bar slash x bar, and so on. So very simply in this case, when the bases are orthonormal, C1 will be equal to dot product of basis 1 with x bar, C2 will be nothing but dot product of b2 bar with x bar, and so on. So this is one of the special case when the bases are orthonormal. Now in the next case, next special case, if the bases are orthogonal. So in that case, as you have seen from the notes, A, the matrix A becomes diagonal. Therefore A inverse also becomes diagonal. And there we can use the orthogonal decomposition theorem, where each C, that is C1, C2, C3, can be evaluated as nothing but each basis function dot product with x bar divided by the dot product or inner product of the basis with itself. This is known as the orthogonal decomposition theorem. Right? So this is the special case of orthogonality, which we will be using a lot in our linear algebra case. And then there is a third case where the vector space V belongs to some r raised to n dimensions with standard dot products. So let G, we are just going to denote some G as the basis vectors B1 till Bk. Okay, and I'm going to claim that A, the matrix A which we have found, is nothing but G transpose into J. Now how is that claim true? If you write G, which is in this form, and if you write G transpose, which will be nothing but the column matrix in this form, and when you multiply G transpose with G, you'll see that each basis Bi gets multiplied with Bj, which is nothing but what happens in the matrix A. Therefore this claim is true that our matrix A will be nothing but the product of the basis matrix G multiplied with the transpose of the basis matrix G transpose. So this is very important in solving the numericals. So therefore now we'll go back to the equation. G transpose G will become nothing but C1 C2 till Ck equal to G transpose x bar, since Bj, that is each component of basis function inner product with x bar, is nothing but transpose of that basis with x bar. So this should be an inner product. So this is the explanation of the projection part. Now let's look at one of the problems. So problems can be solved using two methods. So I'll be explaining both the methods. So the first problem that we have in hand is the vector space is in a 4-dimension space, and W spans these two vectors, right? And X is given to us as 1, 3, 3, 5. So I'm going to denote the two vectors inside W, right? The span is nothing but the subspace spanned by these vectors. So I'm going to call them B1 and B2. So B1 is 1, 1, 1, 1, and B2 is 1, 2, 3, 4. So the question that has been posed to us is find the projection of x bar. That means projection of this x, this should be x bar, of x bar on the subspace W. So let's first find G. So G will be nothing but these two subspaces B1 and B2. So I've written them in the form of a matrix. G transpose will be nothing but this column becomes row and this column becomes the row, and then we multiply G transpose with G. So you multiply this row with this column, and then this row with this column, this row with this column, and this row with this column. So that answer turns out to be 4, 10, 10, 30, right? And then you multiply G transpose with given x. So once you do that, G transpose into x becomes 12 and 36, right? So now using the previous equation, all we have to do is find G transpose G, which is 4, 10, 10, 30, C1, C2 equal to nothing but G transpose into x, which is 12 and 36, right? So this is of the form G transpose G into C equal to G transpose x, right? So we need, the task we have is to find the C. So to find the C, I'm going to bring G transpose G on this side. That means I'm going to find the inverse of G transpose G. So now how do we find the inverse? You first find the determinant. You swap these two elements 4 and 30. So 30 comes here and 4 comes here, and then you change the sign of these two elements. So these two become minus 10 each. Once you do that, you can find the inverse of G transpose G. Therefore C1 C2 becomes inverse, which is this part 1 by 20, 30 minus 10 minus 10, 4 into 12 and 36. Now you can multiply all these factors and you will end up with 0 and 6 by 5. So this 0 represents B1 bar, basis 1 bar, and this 6 by 5 represents B2 bar. That means C1 and C2 are nothing but the multiplying factors for base B1, basis B1 and basis B2. So since the multiplying factor C1 is 0, we do nothing to basis 1, whereas basis B2 gets multiplied with 6 by 5. Therefore PW of x, the PW of x which we have to find, is nothing but 6 by 5 times of B2 bar. So you take B2 bar, which is 1, 2, 3, 4, and multiply this with 6 by 5. Once you do that, you end up with this. The last task that we have is to find x bar perpendicular, which is nothing but x bar minus PW x bar. And once you do that, x is given to us, PW x bar we have just found. Once you do that, you will get your perpendicular matrix, x perpendicular bar. Now how do we check if we are right? You can see that these two are orthogonal to B1 and B2 bar. If you multiply this with B1 bar is 1, 1, 1, 1. Once you multiply this, 1 by 5 cancels, minus 3 by 5 cancels. Therefore, x perpendicular bar into B1 bar is going to be 0. So it's orthogonal. Next, if I multiply this with B2 bar is 1, 2, 3, 4. Once I multiply this, you will see that the answer is 0. Therefore, x perpendicular is also orthogonal to B2 bar. So this is one method of finding the projections. In the next video, I will explain you what is the other method of finding the projections, and that method will follow the notes which I have shared with you.